Welcome to our final DLS for the academic year 25-26. Today we have a special treat. We have from LSU, from our neighboring university, Dr. Aisha Ali-Gombe, and she is going to talk to us today about from assembly to intelligence, the evolution of malware analysis. So Dr. Aisha Ali-Gombe is an associate professor in the Division of Computer Science and Engineering at LSU. She directs the LSU Cybersecurity Clinic, and she founded the Systems Security Lab. And she also holds a joint faculty appointment with LSU's Center for Computation and Technology. Her research lies in the intersection of cybersecurity and digital forensics. She has a particular focus on non-traditional platforms such as IoT and mobile devices. Her work leverages machine learning, generative AI, memory, and binary analysis with software implementation and reverse engineering. The purpose of this is to address applied cybersecurity challenges. These challenges would include malware detection, system defenses, cybercrime investigation, and privacy protection. She earned her Ph.D. right here in Louisiana in engineering and applied science, computer science and information assurance from UNO over in New Orleans, our neighbor to the south. And she received that Ph.D. back in 2017. She is actually a recipient of over $6 million in external research funding. So we are delighted to have her. She has a publication record of over 50 publications. She is well versed in this field, and it is just a delight and pleasure to present to you today, Dr. Aisha Ali-Gombe. So she will come up and talk to it.
I like to drink water. All right, I don't like getting constrained like on the device here. I'm a walker when I teach, so let's see how that's going to work out today. All right, thank you very much for the kind introduction. Can you hear me all the way from the back? All right, like she introduced, my name is Aisha Ali-Gombe. I'm an associate professor of computer science at LSU and also the director of the LSU Cybersecurity Clinic. You've already covered the next slide, but just to kind of recap there, in addition to directing the clinic, which is focused on workforce training and community development, community connection, actually. I also run the System Security Lab, and that's kind of where I do most of my technical cybersecurity research. And so my research sort of falls in 5 different themes, but today's focus is going to be on malware analysis and how we leverage, from reverse engineering to software instrumentation, and then to leveraging AI, in analyzing malware. And so I was kind of thinking, what will be the right approach to this lecture? Like, how do I approach, how do I, talk to you all about malware analysis? And the fact is, in a lot of universities, malware is not necessarily a topic that's been taught a lot. And so I thought, before I tell you what I do in my research, I need to give you some kind of foundation, some basics for malware analysis. I think that's kind of really a nice starting point. So the talk is going to be, you're probably going to see it in 2 kind of different forms. So the first part of the presentation is mostly like a lecture. So it's like, today we're like in, I don't know, do you use CSC or COC? What do you use for computer science? In LSU, we use CSC for computer science. It's like, your CSC 4100 or something. And then the second portion of the presentation is going to be more research focused. I'm going to talk to you about what we've been doing in my research for the past, maybe about 10 or 12 years. All right, so let's start with the foundation with the basics. Show of hand, how many of you have ever been infected by a malware? All right. How many of you have ever seen that malware infection in real time? All right, a few of you. Okay, so I thought it's gonna be nice. Let me record myself. Think about me. I'm kind of a little bit dummy. I'm going to do some website because I want to get some app that does 3D, design. So I went to some website. I had one of this Go.exe. They said it's a nice, application. So I'm trying to download this app. Okay, I downloaded the app and then I'm trying to install on my computer. Oops, my Windows machine USC is telling me that this is from a non-publisher. I was like, yeah, go ahead and install it. Okay, and then there's some kind of weird pop-up somewhere, and it's telling me that there's an error, report to Microsoft. I'm just gonna okay, report to Microsoft, right? So then reported, but then boom, what's happening? Something bad happened. And then there's this weirdly looking pop-up coming up here, right? I mean, I didn't look at that window, something that happened. That is definitely not from it, right? And so if you're in my position, what would you do? What's your next course of action? You're going to restart your machine, right? You all agree with that? All right. I restarted my machine. Oops. Okay, quit. What will you do next? Hard reboot, right? You're just going to hard restart, right? Okay, the machine is dead. All right. So that's malware infection. That's really in action. You see, like that's malware taking over my machine. So that set the stage for what exactly is malware. Malware stands for malicious software. By formal definition, this is an application, kind of software program that is installed in a victim machine with the intent of doing some kind of malicious functionality, violating your confidentiality, integrity, and availability of a victim's machine. Now, for the most cases, malware is installed covertly, but sometimes, again, we go out of our way to kind of like install malware and, not knowing just, sort of malware. But anyway, at the core of that definition is the idea of intent. Malware will always have some kind of intent to do something. And that something is not necessarily what you want, right? What you want to happen in your machine. And so when you take that definition and you deconstruct what is intent, what does a malware want to do, right? Usually that is inbuilt or is embedded in the functionality of the malware. So what we call that is a payload, right? So malware payload really embeds the functionality of the malware, what the malware will do in the victim's machine. And for the most part, pretty much it deals with like everything you don't want to have, right? Somebody logging your key, somebody spying on you, ransomware, all sort of things. I mean, there are so many different kind of version or definition of malware payload. But at the bottom line of the definition of what is a malware is really the understanding of the malware has a functionality, and that is part of the intent. But intent in a malware goes beyond just the payload, because for somebody to design a malware, they have to identify who's going to be the target, right? What sort of machine are we going to infect? What sort of operating system? What sort of device? What sort of network system, right? And then the propagation. How can I move from one victim to another? Is it going to be through network? Is it going to be drive-by download? Is it going to be Trojan? How do I move? And then there's the attack vector. When it reaches the target, what happens next? Is it going to install itself, through some kind of vulnerability exploitation, like is it going to inject itself into some kind of memory or some kind of, a device driver that is running? There has to be that definition of attack vector. So when we take all of that, we're going to see that malware by design will have intent, although we always think about intent as the payload, as the functionality, but it goes beyond the functionality. It includes, the propagation, the target, as well as the attack vector. Now, it's not all the time that when you look at the malicious sample that you're always going to get that direct information about what's the target. Sometimes it's really about, how the malware is designed. Let's say you get a binary packet. It's like, going through the binary packet, how it's going to exploit that you're going to see that it's targeting a specific type of operating system based on what's built into that. So let's go back to my draw.exe, okay? Now I'm not the person that went to, drive-by download and download draw.exe. Now I'm on the other side trying to analyze, trying to figure out what exactly is draw.exe. Is draw.exe malicious, right? So that process of understanding, of finding out whether draw.exe is malicious or not, that is malware analysis. So we think about malware analysis as a technique for analyzing, examining, introspective, binary, potentially of unknown origin for whether it has, malicious component or it doesn't have malicious component. Now, in practice, we think about malware analysis having 4 different stages, right? And you can think about it as a pyramid, right, where we have increasing order of complexity. At the top of the pyramid is what we call manual code reverse engineering, and at the bottom of the pyramid is what we call fully automated analysis. And so this also has historical kind of connotation to that, in addition to being, increasing order of complexity. I'm going to kind of like walk you through the whole evolution and history, and hopefully that ties to the type of analysis we'll be seeing in a minute. But let's start with the top of the pyramid here, where we have manual code reversing, right? What does that mean? I mean, from the name, that this is, we're reversing code, right? How do you reverse code? You cannot reverse code without knowing how to design code, right? So let's do software engineering 101, all right? So how many of you have written Hello World? If you've never written Hello World, you're not a computer scientist. You ought to agree with me, Michael, right? If you've never written Hello World, you're not in this department. So we've all written Hello World. So if I ask you to write Hello World, probably, in C, like 4 lines of code, right? Distribute your main function, just like printf, and then print Hello World, and then return it down, right? You probably write something like this. And then how do you take this program, how do you take what you've written as a source code and get an executable? What process? How do you get an executable from this? I think I need to see, something I just wrote in my notepad. You're going to compile it, right? Exactly. You're going to compile it. Thank you. All right. So we're going to compile it. So what happened in that compilation process? Again, for simplicity's sake, let's assume we're not taking, let's take C, for example, right? We're not taking, Java or Python, whatever. Like there's so many things with different programming languages, and also the different, product or the different output you're going to get. Let's assume we're compiling a C code. We're going to get, the output is going to be something that we can run on your Windows machine. What happened within that compilation process? How many stages at minimum you're going to get? You tell me, like,
You're not certain on how many stages, but essentially you're going to convert it to hexadecimal, right? At the end result.
Hexadecimal?
You go for like personal code, like human read code to machine code, like go to
Right. So I agree, probably that's what you mean by hexadecimal, the machine code. Right? So the product you're getting here, actually, the executable is your machine code. So generally in C compilation process, you're going to have a minimum of 4 different stages, right? The first stage is going to take your raw source code, it's going to expand your source code in the pre-processing stage, where you expand your macro, you resolve some variables, and you're going to have this big giant code, right? Whatever you wrote in, like, your beautiful variable name, like, you're not going to have that after that expansion. And so that's pre-processed. So that is passed to the next stage, which compiles that source code into assembly instructions, right? And that is the actual compilation. And then from there, you're going to take that assembly instruction and you're going to assemble it where needed, right? So you're going to take assembly instruction and then assemble it into machine instructions. And that's really your object code. And then if you have multiple object file, code, because your program is kind of big, you have multiple classes, you're going to have multiple object files, and then that goes through the process of linking, right? And then you get a final executable. So a little bit of, kind of like process. I mean, there's more depending on the kind of compiler and whatnot, but generally, like in your C compilation process, you're going to end up with these 4 different stages, right? So if I am taking my Hello World, which has already been compiled into machine instruction, how do I reverse it? What is reversing here? Reversing means I'm trying to get it into some representation that will make me understand what is built into that executable, correct? So there are 2 different types of reversing. You can do what is called disassembly, which takes the program, and then in zeros and ones, it's going to convert it into assembly. Remember from my previous slide, assembly is somewhere in the middle, which is almost very closer to the final product. So what you're doing is you're taking your final product and converting it into this intermediate representation. Again, for simplicity's sake, I'm not saying you wrote the program originally in assembly. It's possible that the program was originally written in assembly, right? So, but disassembly is that process where you take the program and then convert it into that intermediate representation. And then the other type of reversing, you take the program, because you really don't like to read assembly code, right? I'm going to talk about this a little bit. But you can decompile it completely into human readable, high level source code, right? You can convert it back into C, or you can even think about like transpilation, and you can convert it into maybe Python or something like that, right? So the idea is one converts it into intermediate representation, mostly in assembly, while the other one converts it into high level language. right? So these are the two types of reverse engineering techniques that we have. Now let's go deeper, a little bit deeper into that. Now, what's the difference? For disassembly, the idea is you have this machine instruction, which is usually in zeros and one. Again, for simplicity's sake, we always write it in hexadecimal. So you program first in high-level language, compile it into the machine code. Disassembly takes that machine code and convert it into assembly instruction. And the way it happens is it's a very simple process, right? Where we take each byte and then try to decode it into a valid instruction using the instruction set architecture, right? So if, let's say I have 55, I'm gonna, the instruction set architecture, when you do a lookup, you're gonna figure out, okay, what is 55? Is it a valid opcode? If it is a valid opcode, then what is the next byte? Is the next byte supposed to be an operand? Is it a displacement? Or is it just the next instruction, right? So this is usually, it's kind of a lookup table where the instruction set architecture tells you how to decode the byte. So pretty much you're gonna end up with, something like this where, just keep walking through the bytes. Now, because of that, we say that this sort of transformation or this sort of conversion is a one-to-one mapping. You're not really losing any information. You start from one byte, that byte tells you what to do next, and then if you're done with that instruction, the next byte tells you that's a new opcode, and then you keep going on until you get to the end of the file. Pretty straightforward. Okay. Now again, this is non-lossy. It's very straightforward. It's one-to-one mapping. Decompilation, on the other hand, is a different ballgame. Okay, because decompilation is very complex. It goes through the process of taking the code, disassembling the code, walking through the code to find out different routines, and for each routine you're going to identify control flow, data flow, and all sort of things, and then results and variables using the symbol table, and then keep going back in iteration until you can decompile everything. Okay. Now, because of the complexity that goes into this, and because already from your compilation process, you already have optimization in the compiler, you have a linker optimization and whatnot, almost certainly that this is a very lossy process, and you're almost guaranteed if you have a very big program, you're not going to recover the entire thing. So maybe some routines will be compiled correctly, but some routines will not be compiled correctly, right? So in general, when we do malware analysis, when we take these two techniques as the only techniques that you can have in reverse engineering, generally we go with disassembly as the favored technique, and then where the program becomes very, very complicated, we can supplement that with decompilation, hoping that the decompilation is correct. Okay, but we don't usually just take in decompilation as the only technique. We kind of like use them, as a complement. Now, let's assume, okay, at this point, you all understand what is reverse engineering. You're all malware analysts at this point, okay? And you're given a sample. You can analyze it using these two techniques. You can read the assembly code, or you can kind of decompile and read this code, right? What do you think is the major challenge of this approach? If we had to analyze all the malware in this, fine, okay? Human error. Why do you say human error? Because when we read, we're reading code. Okay, let me ask you this question. How many of you have ever done a group project, a programming group project? Almost everybody does it, like your student, right? How many of you have ever read your friend's code? How many of you enjoy reading code? Yeah, I expect this, right? Because reading code is hard. Like it's very hard. Like if I do a group project with you, we agree that okay, you do this function, I do this function, you do this class, I do this class. Probably you never read the other, right? You just agree with whatever they have and just like plug it into your program and hoping that it's all going to compile correctly, right? Because reading code is hard, right? And because in general, like designing program and putting all this logic into program is very complicated, and so code complexity is the major problem. And again, when you think about code complexity, because reading is hard, reading code is hard, and the code is very, complex, it takes more time, right? So I agree with you. All right. So let's kind of go deeper into code complexity. I showed you an example that we can decompile the hello world, right? Even if you've never read assembly instructions, you probably will read this and understand that this is hello world, right? All right. But this is not the reality. Can you read this code? So it will take you a crazy amount of time, even for seasoned analysts, for them to understand just one single binary. Like it takes crazy amount of time for reverse engineering. Additionally, with malware, they're not designed for us to understand. They are designed to potentially be obfuscated They come with encryption, encoding, all kind of jump insertion. The design with very complex, hard to understand routines, and they sometimes have self-modifying code. So it's not easy to reverse and just say, okay, we have a tool, we're going to reverse and we're going to understand it. It's just very hard to do that. And so because of that, that led to the second part of the pyramid, which is interactive behavioral analysis. Because we know that if we had to analyze all the malware in this world, it is not feasible to do that only with reverse engineering. Okay? Now, in the second technique, slightly different, where if I think about having a sample, instead of like me going through gaps and gaps and gaps of assembly instructions and kind of just reading code, how about I do this? How about I take that program and just pass it into a debugger, right? Have you ever used a debugger before? Right? What do you usually do in a debugger? What's the first thing you want to do? Oh, what is it? Debugger helps to debug that code. But we use debuggers for the most part because you can single structure your instructions, right? You can see exactly if I step through one instruction, I can examine the registers, I can examine memory address, I can see the program behavior, right? That's really why we use debuggers, because you can control execution. Normally, if you just execute, normally you don't control the execution. But with debugger, you control execution, right? So I can take my malware, just just run it in some debugger and just try to see what's going on by examining all that stuff. I can even plug in another tool, to do like network analysis, where I can kind of like see how the malware is communicating with the external entities. I can even try to explore to see if the malware is creating files, it's talking to the registry, it's creating new handles. I can even look at the Explorer to see whether the malware is creating other processes, creating new threads, what is the working set, the size of memory, and whatnot, right? This is interactive behavioral analysis. So for formal definition, this is a type of analysis where you run the binary in a contained environment while monitoring behavioral data. Classical difference with manual code reverse engineering is the fact that with reverse engineering, you don't run the code. You read the code, right? With interactive behavioral analysis, what do? You run the code in some kind of contained environment. Again, this is contained in quotes because you have to do a lot to contain it, right? I'm going to talk about some of the issues here, but the definition has to mean some kind of container, right? So you run it in some contained environment and then monitor the behavior for now. And there's so many different tools to do the monitoring. Okay, so now assume we have two tools, right? We have kind of two pathways or two different techniques. You can do manual code reverse engineering. You can also do interactive behavioral analysis. Now, can you tell me what are some of the challenges of IBA? What are some of the challenges that come to your mind? If you are to do interactive behavioral analysis, what do you think are some of the challenges? Time, okay, time. Because you don't know what you're dealing with, right? Remember, it's a binary of unknown origin, so you don't really know what you're heading into. Like you might start to run something, you're just gonna keep running forever, right? So time is a real challenge. What else? All right, so let me give you a cheat sheet here. So assuming, I'm doing research in this university, and this is my lab, and I'm running, some malware. I have no idea. I just got it from the lab, okay? And then maybe my container is not really a good container, right? Maybe, it has some really bad network policy. I just run the malware here, not knowing what to expect. What do you think is the risk to the university? Risk of infection, right? Right? In fact, at LSU in my lab, it's always like, we have like about 40 terabytes of malware. And sometimes, it's kind of like, we don't put it on the network, but sometimes like students copy some samples on their machine, and it's always like we're getting calls from like ITS, like we see some suspicious stuff going on in your lab. Like, yeah, we know about that, right? Because they can see the signatures of some of the samples because they have this continuous scanning, and they see that we don't want the samples within our network, right? So risk of infection is one major concern, but additionally, some of the samples they come with what we call anti-analysis, where the malware knows that it's running in some container, it's just not going to execute the behavior. So what happens? Think about just a simple logical instruction. If I'm in a sandbox, exit. Else, infect. Right? Just simple logical stuff. So malware can just run some checks, know that, okay, I'm in some kind of virtual machine. I can just check to see what are the device, your network, device name and whatnot. If you go to your control panel, you can kind of see if you're in a VM, everything's like VM underscore something, right? If I'm in a VM, just don't do anything because that is a container, right? Don't do anything. So the malware has an entire. But on top of all that, sample diversity is another major challenge for this kind of analysis. Why? Let's kind of like go through some kind of type evolution for malware. So you see, when malware started somewhere, I mean, probably much older than me, but like assuming, just going back to like the 80s and, maybe early 90s, right? Malware wasn't really criminal. Malware was basically, y'all Southeastern are like great in programming. LSU also great in programming. Like, okay, who's going to be the best, right? So we're going to try to hack you. We're going to try to hack us, right? That was really how it started. It's like, just kind of friends doing their own thing, right? And then, just flexing their muscles of who can program better, who can get into another network better. That was how it started. And then gradually it moved to what is more called like a hacktivist kind of thing, where people want to make political statement. In fact, the first ransomware was released in 1989. It's called the AIDS ransomware, where some doctor was just not happy with everyone with some friends and just decided to spread a floppy disk containing a ransomware. If you just plug it on your machine, for all the researchers, then you just take over your machine and ask you to, send some kind of, I think, $130 to some, bank in Panama, and that's it. Like, it was kind of, for him, he was just trying to make a statement that he was raising funds for AIDS research, right? I mean, whether it's true or not, but that was kind of the claim. But hacktivism was a major thing at the beginning. But then gradually it moved from that to more criminal entity, to more kind of, organized crime, malware as a service, and now what we have is cyber warfare, nation-state actors, attacking each other. And so in terms of payload as well, we started, if you go back to maybe old cybersecurity textbooks from the 90s, what you will see is definition of malware is like viruses, worms, right? Then gradually we moved into Trojans, and then gradually that kept moving into, now we have ransomware, and now what we have is advanced persistent threats, or APTs. Okay. Now also with the change or evolution in technology, I mean, y'all remember like when mobile started? I mean, it feels like mobile has always been there since forever, but it's just like a few years ago. But then today we have IoT, we have mobile, we have cloud computing, and each of this new technology brings a new challenge, and definitely also new types of malware, and obviously new kind of payload, right? So this sort of type evolution, if you put it in the context of interactive behavioral analysis, it means creating the right environment for each of this malware to run. It's a hard problem, right? Because mobile malware will run in a different container than the Linux malware, than the Windows malware, even the version, as you go from Windows XP to today, like, if a malware is supposed to run on Windows XP, you're going to run it in Windows 11, obviously, right? So that makes creating interactive behavioral environment much more complicated than, we want it to be, right? So with that, I want to introduce the next stage. So this next stage is really not there to kind of deal with the challenge of the previous stage, but rather it's just kind of an addendum where we want to find a way that we can quickly identify what sort of sample is this. Without going into manual reverse engineering, without going into interactive behavioral analysis, can I be able to just immediately just search something within the binary to say, yeah, this is Windows malware. Yeah, this is Android malware. Yeah, I've seen this sample before. Just some kind of like, a search, but not necessarily deep analysis. And so some example of this technique include program introspection, where we can look into the header of a file, see that, okay, this is the PE file, so definitely this malware is geared towards Windows. And then you can find the specific architecture. Maybe, yeah, this is geared towards x86, this is geared towards 64-bit. Oh, this is geared towards, ARM architecture. So you can get, sort of like, okay, with this, I know how to analyze this malware, but it doesn't tell you a lot more than that. Now, you can also run things like strings on a program. If you almost certainly, like, you can try this later. If you take any program and run strings, our programs by design, after compilation, they have a lot of human readable strings. But if a program is encrypted when you run strings, you're going to get a lot of non-human readable strings. So with that, you can immediately say that, yeah, that program is definitely certainly obfuscated. We cannot analyze it statically. We probably have to run it in a debug, right? So it allows you, make certain decisions almost immediately. You can also look at imports. Every program, like when you write program today, you always suddenly will make some API calls, right? Some system calls, right? And those system calls say something about the design of your program, about the functionality of the program. If I'm analyzing a binary and I see something like, you know, an API that is accessing keyboard, I would automatically say there's some keylogger happening with this binary, right? So it will help fine-tune my database. Additionally, we use program hashing, where if we analyze, let's say, you know, 1 million samples, we can take hash of these samples, and then, you know, tomorrow, if we get a new sample, we're just going to compare this hash of the new sample with what we have. If we, you know, it's the match, then we don't have to reanalyze because we've already analyzed this before, right? So that's just, again, a way of just immediately getting some information about the malware without spending too much time. Okay, now let's go back to our challenges. We talk about code complexity, infection risk, anti-analysis. We talk about sample diversity, right? But additionally, we started to see kind of like, you know, more malware started to create what we call variants. And because of the creation of variants, we're seeing like growth and explosion in the entire, you know, kind of malware space. And let's kind of go deeper into variants. What do you think is a malware variant? What does that mean? Anybody ever heard of that word? All right, so variant is really sort of a strain. I'm thinking about it like a, you know, a virus, like a strain of COVID-19, something like that, right? So it's a strain or a version of a known malware, usually that will have sort of different appearance, but they maintain the same behavior. In some cases, the logic and the structure may change, or it may not change. So there are so many ways of creating malware variants, and, you know, some example here is repackaging, which is very common in the mobile world. In repackaging, we take a benign application and we're going to take a malicious data that we're going to inject it into that benign application. Then the product after that is going to be what? It's going to be a Trojanized benign application. So when you take that, let's assume it's a game app, I think it was very popular on mobile devices around 2015, 2016. So when we take a game, from, in fact, it was infected even the primary market. So you can download a game from Google Play, you will know that it's Trojanized, and then you install it to still do the main functionality, but you always have some kind of covert functionality, which is the malicious function. Another way to create a variant is polymorphism and metamorphism. And so with polymorphism, you know, it's really, there are some tool set that allows you to create a strain of the same malware that has completely different appearance, but maintain exactly the same logic, right? But, you know, the appearance, like when you run hash, they're different. But then, you know, that the structure and logic is the same. Metamorphism, on the other hand, is sort of like the same as polymorphism, but it changes within the logic. Behavior remains the same, appearance is different, logic is different. So you have a different strain, and which is much more stealthier and can throat analysis compared to repackaging and polymorphism. And so because of that, again, I mentioned that we see more growth in malware. So when you look at the malware growth from the 90s, you can see that already in the 90s, we have a few hundreds to a few thousand, and then that kept steadily growing, you know, upward to a few thousands. And then up into the new millennium, we're having in billions of samples, right? So that's kind of really it's growing exponentially, right? And so what does that say? Let's go back to our pyramid. That leads us to the last part of our pyramid, which means now, because of this growth, we really cannot depend on code reversing alone. We cannot depend on interactive behavioral analysis or static inspection. We need some kind of automation where we can, you know, go beyond just static or just go beyond a simple dynamic to more using intelligence in identifying immediately this is a malware, right? So think about what we have today in terms of EDR, in terms of network intrusion detection systems, right? So all of these, they try to identify if we have some kind of intrusion, if we have some kind of malware, using more of intelligence than using, you know, sort of like the more static or simple approaches that we have before. So let's go deeper into that. At the top of automation for malware analysis, you have what is called fingerprinting. And so in fingerprinting, I mean, it's like the name implies, if you have my own fingerprint and tomorrow I'm here logging in, you know, coming through the door, put in my fingerprint, if it is a match, then it is me, right? If it is a match, it is not. And that's the same thing. So with malware, we can go beyond using simple hashes to create a more complex fingerprint for malware so that we can be able to identify the malware even if it is a new strain. As long as it is maintaining functionality, we should be able to say that, yes, we've seen this malware before, although now it's, it's a holomorphic version of it, or it's a metamorphic version of it, but we are identifying that. On the other side, it's also possible that, we may have zero-day attacks. We may have something completely new. We don't have the signature for it. Can we be able to get, say, given the binary of unknown origin, we don't have a signature for it. However, the way it is behaving or the way it is structured is more likely malicious than that, right? So some sort of anomaly detection. And so at the core of the fingerprint to anomaly detection, you're going to have features and feature engineering. And so you're going to need to extract, some kind of artifacts from the program, and that will help you create that information. So artifacts could include extracting byte sequences, output sequences, network artifacts, system artifacts, binary characteristics, and whatnot. And so, interestingly, all of these artifacts cannot be extracted without the top of the pyramid, right? So if you want to extract output sequences or byte sequences, you're going to need manual reverse engineering. If you're going to extract network artifacts or system artifacts, you're going to need dynamic analysis or interactive behavioral analysis. If you want to extract system file characteristics, you're going to need static properties inspection, right? So you can see in the whole sort of pyramid work in tandem instead of like, we're not going to use this, they sort of work together at the bottom of the pyramid, right? And so there are most of the time when we create tools for that are sort of automated analysis tools, they use sort of mathematical modeling, primarily using statistical analysis. And so statistical analysis is mostly used for fingerprinting, and there are multiple different research work that have used all this different kind of distance measures, from Manhattan distance, Euclidean distance, cosine, and whatnot. But also we are beginning to use more AI models, which can go beyond just detecting what we know in terms of malware that we know, but also predicting malware that we've never seen before. So we can use all sort of AI models, from supervised, unsupervised, semi-supervised, and whatnot. And so that's the foundation. That's a lot, right? That's an entire semester, presentation in 25 minutes. All right. So that's sort of the foundation I want to build before I talk to you about, what I do in research and like how we kind of move the frontiers in that space, and kind of like innovation within the malware analysis space. So I want to talk to you about some of my research work. And I started, so when I went to University of New Orleans, honestly wanted to do database as a kind of my Ph.D. dissertation. I met a faculty that was kind of great in computer security, and I felt like, oh, this is interesting. I'm very curious. I want to do this stuff. And so I started with sort of forensics for my master's, and then gradually, really love malware. And somehow I'm kind of like the weird ones that really love to read code. So I started reading code, and I thought like, this is awesome, right? I don't like to write code, but I love to read code, which is very flip. But anyway, so around 2012, that was kind of really when I started getting into malware analysis. And 2012, Android was a baby. You all agree with me, right? When was the first Android device? Anybody remember?
No.
2008. I mean, conceived 2007, gave birth 2009, 2008, right? So around 2012, we started to see like explosion in Android malware. Mostly because, again, there's a lot of like, easy way to repackage and create new variants. And so variance detection was one of the major. It's like, okay, we're seeing just like this astronomical, new malware landscape, because before then it was mostly Windows malware all through. And then all of a sudden, everybody was excited about mobile and smart devices, and now we can talk to each other. I can talk to my family all the way, in Nigeria and whatnot. But then, now we have this significant problem where, malware is just taking over this stuff, and we can, even when you go to primary market, like you can easily be able to download like Trojanized malware. And so I started researching into that space, like what kind of contribution I'm going to make here, and this from the basis for my PhD dissertation. So my algorithm was kind of looking into how to create effective fingerprinting using both structural and behavioral features. However, I didn't want to do at the time dynamic analysis. So I want to get my behavioral features from static file without doing dynamic analysis. I know that I can get the structural features from the static file, but I also wanted to get the sort of behavioral features from there. So the way my tool works, which I call ACSAC, is it takes an Android application, it disassembles it, and then identify what I call suspicious functions. And so think about suspicious function as a malware is a game voice, it has an API that sends SMS. Right? So I identify those, kind of like dangerous APIs. I term them as suspicious APIs. So I look for where they are called. So I take that caller function and then extract the output from that caller function, pass it into some kind of normalization function, and then, extract n-gram sequences and put that as some form of pattern, and that saves you as the structural signature. And then for the behavioral signature, Android keeps what is called the permission list in the manifest file. So I can extract that because the permission tells you what the program does, right? So if the program is, connecting to the network, is reading your device information and whatnot, you see all of that in the permission list. So I extract the permission list and add to the output sequences, and that forms the signature. And so at detection time, if I'm given a new sample, I'll collect its signature and then compare to the signature that I already have using 3-level similarity matching using targeted overlap coefficient. So I start with the pattern level n-gram matching, and then if whatever the result is, all the functions that we're able to match, pass them into function level matching, which aggregates those functions, and then into the final similarity index, which is a function of the function level matching and the permission overlap, and that becomes my final similarity index. Of course, there's a lot of optimization that goes in. There's also deciding what's the threshold and whatnot. But at the end of the day, this tool achieved about 98.9% accuracy with a very small false negative rate, which is your misdetection. So in our analysis, you always want to get a small misdetection. So which was kind of doing what it's supposed to do. But we wanted to also kind of like push a little bit to see how about if we add some kind of obfuscation, right? Because generally static analysis is not good with obfuscation. How about if we take some function, we pass it through some kind of modification tool that changes every function call to like encrypted class name or encrypted function name or encrypted variable name, and then we also added like jump reflection and then jump insertion, and then test it to see if this tool can achieve the same sort of accuracy. So it achieved 100% accuracy for this test case, and it was doing way better than Dread Legacy at the time, which was the state of the art tool, and was doing way better than the best antivirus. We kind of pushed again to say, okay, how about if we have multiple layers of obfuscation? Well, we added like encryption and reflection together and whatnot. And again, this was achieving a much better detection rate than you have in the other tools. So kind of great, it's doing what it's supposed to do. However, it has a huge limitation, which is the fact that if we have more dynamic obfuscation, let's say the malware is loading dynamic class, and if anyone of you are programming Android, under programming, right? So Android allows you to load that class at the front, right? So you can kind of like do dynamic classes. So I can install an app, but the app will not have, I can have one entire class or even package that is not just completely missing from the program, but I can call the class to load it at runtime. So then when you look at the class, statically you don't see the class, when you look at the package, you don't see that class statically, but then at runtime it's going to load it. And then if it is a malware, it's probably going to load it in memory, do whatever it wants to do, and then delete it from memory. So you never see it on disk. So limitation, it cannot detect any kind of dynamic obfuscation. And when you have a 0-day sample, because we're based on fingerprinting, it doesn't detect 0-day sample. So that was kind of a limitation. And again, because this was part of my PhD dissertation, I wanted to add something more. I mean, my professor is not going to allow me to graduate with that. So I was like, okay, let me try to do more dynamic analysis. I ran away from it at the beginning. I was like, I'm not going to do dynamic analysis. But I was like, okay, let me get into that. So I kind of started to learn instrumentation. How many of you have ever learned about instrumentation, software instrumentation? Yeah. So instrumentation in general is a way of it's a way of finding out within a software. You can take another program and kind of like inject tracing code. Pretty much a software instrumentation that's what it does. So if let's say I have a program that I have no idea where it's coming from, I can define things that I want to know from this program. I'm going to use instrumentation tool to inject traces for that, whatever objective I have in mind. So in my own case, the objective was I want to know if a programmer unknown already has made any suspicious calls. Okay, I want to trace what this call is, what the parameters were passed, and what's the return value. I also want to trace data flow. So if I have a function that reads, let's say, device ID, I want to follow that device ID and see if the device is sent to the network or is reaching to the file. So I want to do some kind of propagation, right? And I also want to check for some other suspicious behavior, for instance, if it is loading a class at runtime and whatnot. So I built in this instrumentation engine that allows me to follow the program, but I was using static instrumentation, so I had to take the program, inject this monitoring code, repackage the application, and then run the application at runtime while I'm exercising it, and then it's going to be logging whatever I added in the instrumentation. So that way, instead of a dynamic analysis, I'm adding the check statically. And assuming I have a dynamic class, my instrumentation at runtime is going to stop the program from executing. It's going to query that dynamic class, send it back to my analysis machine, and then I'm going to repackage that file and send it back again, and then the program continues to run. So it's sort of a hybrid analysis, if you will. And so with that, again, this was not using more intelligence, like in terms of like statistical analysis or AI, but it was more in the dynamic analysis space. It achieved 100% accuracy for sensitive API monitoring suspicious behavior, but about 94% accuracy for the data flow analysis, because it was very complex data flow analysis, especially with malware. And it has a very minimal runtime overhead. Runtime overhead is very, very important in dynamic analysis, particularly in the mobile space, because if your program, you probably have noticed this on your devices, maybe not new generation devices that have a lot of RAM, but in old generation devices, if your program is taking too much RAM, what happens?
Slows down.
It's probably your system is just going to restart that application, because we don't allow, by design, mobile device are designed to be more usable. So if the application is taking too much resources, the system just restart that application. So we don't want the system restarting our target application while we're examining it. So we want to make sure that the overhead is kind of really minimal. So for that, like, it was kind of like acceptable, but we could do more better in terms of memory overhead. But with that, that helps me with that and other stuff. I was able to graduate my PhD, but I know there are limitations. This is a very time-consuming process, right? We talk about time, and it's also very complex. Like, building instrumentation is not the easiest thing. Like, in fact, at some point I was like, why did I even get into instrumentation? But it was fun, but it's very complex to build the right instrumentation tool. But anyway, fast forwarded around that time, AI was started to become like, more common within the Android malware, generally in malware analysis, and largely because with AI compared to statistical analysis, AI has better complex recognition or pattern recognition. It has better feature engineering, and you can, it has better accuracy as well as scalability. And so I thought I did this dynamic analysis, but I would have extracted dynamic features and built a more intelligent system. So I kind of kept thinking about, there's something I could have done with the results from my PhD. And so fast forwarded to 2023, I built something called RGB MEM, which was using CNN model for analysis. But honestly, at the time, there were like, I think, between 2015 to 2023, there were probably more than 20,000 publications in like AI for malware analysis. So like, it's everywhere. But the major problem is really not the model. The problem is really the feature and the feature engineering. So I thought, how can I use a different feature? Like, what sort of feature will I use that's so different and probably will give me some new sort of, matrix? And so I did some work in forensics, mobile device forensics, where we built a tool that if you dump an application memory, we can reconstruct the objects that were allocated at one time. You all know object allocation from Java, right? So all the objects that have been allocated at one time, we can reconstruct that, and with about 90% recovery rate. So I was like, okay, if I can take a memory and recover all the allocated objects, how about if I take those allocated objects and use that as my features, right? So that's kind of what we did. And but instead of just passing the features to a CNN model, we give every object kind of a number within the RGB spectrum. So it's kind of like a color, and we change that into an image processing problem. And so we built the CNN model for that, and this sort of have about 95.98% accuracy for detecting malware within the features, right? But again, there were so many works in the area of using AI for like automating malware analysis, but at the time, the major bottleneck is, and I don't know if some of you are in the machine learning sort of AI space. One of the major problem with AI system is they're sort of like a black box, meaning it can tell you that this is a malware, this is a banana application, but it cannot tell you why. Like, why are you making that decision, right? It's just like, there is no reason, like you cannot be able to explain or backtrack. It was very hard to, there are so many, there are other research that, find a way to like go into the neurons and like extract, some information to say, okay, this is the reason why the decision was made, but it's not clean, right? So explainability was a big problem, and backtracking to figure out the chain of thought. Why, if you said this is a malware, why? Like, why exactly is a malware? So that was a big problem. And so fast forwarded to the time of, now we're in generative AI, we have more advanced machine learning that can be able to generate, content. And so I thought, wow, this is great for me, right? I can actually go back to my roots. I can go back to my initial idea of static malware analysis that I did with ACSAC. But instead of taking the functions and extracting output sequences, I can take each function and just pass it to an LLM and say, summarize and tell me what this function is about, right? And then I will aggregate all functions from a class and that becomes a class level summary, and then aggregate all the summaries from a package, and that becomes package level summary, and I can make a decision about the package, right? So we call this hierarchical summarization, and because it helps us do more classification, but also help us with explainability. And we added some kind of advanced prompt engineering here. We designed 3 different models for this. There's a vanilla prompt, which is like, okay, you're just a malware analyst, tell us what you think about this function. There's also the API scope where we say, okay, this are the APIs, mostly used in malware. Tell us what this function is about. And then there is the malware scope where we say, okay, malware in this mobile space looks like this. Tell us what you think about this program, right? And so we find that the malware scopes did way better. Of course, it's a very abysmal accuracy compared to like the other accuracies that I've reported. But what is more interesting is the fact that we have a great chain of thought. Even when you have a misdetection, you can go back and say, what is the package level summary? And then go back from the package level summary, track back to the class level summary and say, what did each class say? And then go to the function level summary and say, well, what did each function say, right? So you can see there's a clean chain of thought, and it tells you a lot about the malware than we had before with all statistical similarity as well as with traditional AI. And so we did that, and this was kind of published in 2024, and this was actually an honors project by my undergraduate student, which was kind of neat. So in 2025, and this was a work with my colleague and in his lab, we thought everybody struggled with disassembly, right? Nobody, I mean, we struggle with code reversing. We said it's a code complexity is a problem, but also reading assembly is like maybe 10 times harder than reading C code, right? So how can LLMs today help us read assembly better, right? So that was really the task here. Whether it's malware or not, we wanted to be able to read assembly. And so we decided to come up with 5 different tasks and say, there is a code intent. If I give you a block of code, can you tell me what intent this is? I can also give you just a class file and say, give me a header comment, like we usually do in our program. I can also do like a inline comment or code completion or Q&A. So those were our tasks. And the idea is with malparse, for instance, we're summarizing, we actually did the summarization using OpenAI, right? OpenAI OpenAI is trained with like billions of parameters. So like it's kind of like, you know, it's much more stronger than local models. But in reality, with malware analysis, they're very sensitive, right? If you go to DOD, nobody will allow you to use OpenAI for malware analysis. That's just the truth. Because today everything is like nation state, and like even if it is not nation state, like malware is very sensitive to analyze with Claude or OpenAI. So how can we leverage local models for this sort of analysis? So that was kind of one of the research question here. And so we took some few local models, examined the base models, and then fine-tuned them and see, you know, whether we can see some differences between the base models and the fine-tuned models in some of these tasks. And here, the Quen 2.5 for the 7B did well in terms of both of the base model and the fine-tuned model, as well as the code llama. And we also measured, like, you know, we use the cosine similarity in this case as our baseline for the quantitative analysis. And also for the specific task, we found that, you know, code intent for code llama is the best. It's actually, when you use code llama for this, it can tell you, just give a block of code, it can tell you the intent with a better accuracy than the others. However, there is no clear winner here in terms of all the other models. But what this clearly shows that we can train local models, even though, you know, they are trained with, like, you know, small parameters, but when we fine tune them, they can do better. And that can, you know, help with understanding assembly particularly, and that can push the boundaries for malware analysis. Where when we go back to our basic at the top of the pyramid is really the tool that we want to use, but it's very hard to do because of code complexity. And now with LLMs, we can be able to figure that out. So that's really where this research is. And again, we are pushing more boundaries here. And Justin is doing some great work in quantum malware analysis and, you know, doing all the fine tuning and whatnot. Great work as well. Okay, so the last one, I promise you. This is the most recent work. It's currently under review. I don't want to talk about things that are not under review, but this is currently under review. And so the idea here is, how can we use LLM for dynamic analysis? I mean, we've been talking about like using statistical similarity in AI, but mostly like in the static analysis. Can we use LLM to aid just that dynamic process, right? It requires a lot of engineering, because you're not just looking at the code, you have to engineer the process of loading the code in a sandbox, running the program, and then back and forth, because it's probably not going to be one iteration. So the idea we have is, when a malware is heavily, you know, obfuscated and has some kind of anti-analysis, when you run it in a sandbox, it's just going to stay dormant. It's not going to do much. Like, it's probably just do some checks and then, oh yeah, I'm not going to do anything. There's nothing to do. I'm just going to stay dormant, right? So how about if we take that trace and the malware and pass it to a model and say, yeah, this malware refused to run. Okay, can you look at the trace and tell me why, and probably create some kind of rule that's going to override the execution of this program so that it's going to push it to run, right? So we did this, and we created a system called Able. And with Able, you take the trace, you pass it to the model. Model is going to look into that and say, okay, yeah, I think it's not running because it's checking for this, this, and that. But this is how we can bypass it. It's going to create a rule for you. Then you pass the rule back to the sandbox with the malware, and then run the rule and the malware together. For the most part, we found that in our first iteration, it will fail again. And then we collect the new trace why it fails, and then send it back to the model and say, now, that didn't work. Can you think again? So the model thinks again, and then send it back to us. And then, you know, sometimes more than one iteration, but sometimes it works in the second iteration or the first iteration. But we're pegging it about 3 iterations, and almost all our samples actually did run from the 3 iteration. And this is completely without human in them. So all of this was so engineered that, like, you don't need a human there. All like the collecting the traces back and forth, sending and starting the sandbox, all of that was done in an automated fashion. And we compare that with some of the state-of-the-art sandboxes we have, Dual Sandbox and Cape Sandbox, and we can see that if we ensemble, you know, local models here and run this, we can achieve a better detection rate. Now, if we're only using single individual local model, this is not doing better than the state of the art. I mean, local models are not really strong. However, if we ensemble 4 models, we see that, you know, our accuracy is way better than the baseline. So again, this is currently an ongoing work. We just completed it, submitted for publication. It's still under review, not yet accepted, but we're very excited about this. All right, that's a lot, right? All right, but we're doing more. Okay, so I'm not going to go into that, but We're building automated AI sandbox that just completely, take over the decision of analyzing malware. So you don't have to make a decision whether you want to use reversing or you want to use static analysis or automation. It's going to automate the entire process and make that decision for you. We're also building a tool for malware constraint analysis, so we can see what constraint will make the malware run. Because if you don't know the constraint, then you cannot build the right environment. So knowing the constraint allows you to build the right environment. And we're also building an entire malware browser infrastructure that allows sort of like a research across multiple universities, but plugging in everything that we have built before into like the entire ecosystem. All right, takeaway. This was where we started, and hopefully this is where we are right now, right? All right, so we talk about, the pyramid of stages of malware analysis, starting from, code reversing to interactive behavioral analysis to static properties inspection, and then finally to automation. And now, there are even more better tools that are pushes the boundaries in automation. And before I kind of, give back the mic, I wanted to acknowledge my students. Justin, you missed the mic, you missed the gist yesterday. You didn't bring your picture. So I asked everybody to bring their picture. I need to acknowledge them. All right. These are the students currently working in my lab and some research associates. And yeah, that's all I have. Thank you so much. Questions, please. I'm going to have some more.
Yeah, like how do you
So, good question. The first thing is, if you don't want it to infect your device, then you probably want to use some kind of an efficient container like Docker, right? And then you're going to build a policy around the Docker so that like it doesn't split out, right, into process to that. But generally, in terms of building a container for analysis, you build it on a virtual machine because you want it to affect the virtual machine. Infecting the virtual machine tells you what it's going to be doing within the environment. It's going to tell you what process will be created or how process will be created. Then it'll be telling you the parts that will be created, crashing what the processes was going to be done in memory bucket. If you build it within a Docker container, you're not going to be able to monitor that the process will be. That's not, you're not going to get the understanding of the entire malware behavior to allow it to be just like that use. However, not all that use, right? Because you definitely need a strict network policy so that it doesn't slip out of the machine. Now, in terms of network policy, there are so many containers out there. Even for the network policy, if you make it very, very strict, think about like malware is running, malware needs to connect to the CNC server to download a payload, right? And now you have a strict network policy that cannot communicate outside. Then the malware does not exhibit its behavior, right? So what do you do in that situation? You build a policy where the malware sends the packet, you inspect the packet at probably the network layer, depending on where you do that. But you build a policy there, you inspect the packet, you make some changes, and then send it to the CNC server. Then when you receive, you probably can make some changes again in a way that it doesn't steal, right? And so that way you monitor the behavior better than like the complete total company. Does that answer your question? Yes.
Yeah, that works. How would you isolate an incident like this happening to
Me as a person or me as an analyst?
you as a professional?
I would trust my Mac that has a good defender. But the thing is, every site you interact with, every app you interact with is a potential malicious behavior. It's a potential malware. You don't really, as long as you don't know, you're not going to take away the fact that there may be some potential malware being into that. So for the most part, like everyone else, honestly, like what you need to do is make sure that you're not going to the wrong places. Obviously, right?
You don't want it to complicate.
Okay, so if it is me as a person, I'm trying to protect myself first. I'm not protecting anyone else. Me as an analyst, as a researcher, I'm trying to protect the university, right? So as a researcher at the university, when I started at LSU, they actually put me behind a firewall Literally, they're like, no, they just asked, like, it was in a discussion with the ITS, they're like, yeah, what are you doing here? We said, like, yeah, we have, other things. Like, yeah, we have this number of hours, we're going to be doing more. I said, like, okay, you're going to be out of the firewall. But that was very hard because then we want to access, all the machines and whatnot. So what my students do in terms of analysis is we connect the server that contains our malware to the VM. So the server itself is not part of our network. Now that I beg them and now I'm within the firewall. But so the server itself is not within the firewall, but we connect it within our network so that they can access it from their VM. They don't have to access it from the host device. So that's sort of when they download the malware, if it's within the VM, and we contain the network within the VM so that they don't see it. Because otherwise, anytime ICS see that, they'll just remove it. And you could, in practice for analysis, you could neutralize a sample in the sense that, like, first, like, do some kind of static analysis and then remove the component where, like, if it is connected to other devices or like it's propagating, so neutralize the propagation function, and so it's not going to propagate to other devices, right? Because network is like one of the areas of like network propagation. So many different. I don't know what to say. Yes.
So one question I have going to sample the malware and AI, is it possible, like, would it be possible to use AI to like mix an AI with a malware sample for it to look deeper into the malware and see if you can like easily replicate the malware by itself just using an LLM?
So you mean replicate as a propagation or like recreate it inside?
Recreate this.
Okay, so I mean, this presentation is me as a defender showing you what we do in defense. I'm telling you like what they do in the offense side, like the malware offense. It's a lot. They are using LLM much more. In fact, recently we had a speaker came from California, and she's kind of like her research work is looking into this sort of ransomware group in .NET, and she's like, the way they're using LLMs for like creating malware. I mean, before it's a hard network to create a malware. Like I can tell you this, it's harder to create a malware than to create a open app. Even as complex as your cloud application, it's much more complex. But now with LLM, it's much easier for them to create new ones, and it's much easier for them to create even more complex apps and even more complex areas. So, like, while it's helping us on the defense side, on the other side, it's helping them create new samples that can be put. So again, we're just gonna continue this work. But yeah, they could do the same thing with doing. So they're trying to know the malware, they're trying to do something. And think about open models, like virtual models. If I am designing a malware and kind of like putting an adversarial hat here, if I'm designing a malware and before I release the malware, I'm probably going to try to see what does OpenAI say about malware, right? Well, I'm probably going to do something with ChatGPT, you give part of the sample and just like see what the response is, and then that's going to help me create a much more even stealthy version because I know that you probably will.
I'm looking for a silver lining here. So with the offense side, using LLMs a lot more ineffectively, are people on the defensive side starting to see similar patterns pop up where since they're using some of these slightly large language models, similar solution, similar attack vectors, similar payloads, and they're going, oh, we found that, I've seen that before, and they can defeat it very quickly. Well, maybe not very quickly, but more easily.
I can't say, yeah.
Lazy attack.
I get it. I think, if it is kind of like lazy attack, it's kind of like the simple attack, I mean, so LLMs are really rigid. They train on what we already have on the internet, right? So they're rigid on what we already know, right? So in that sense, like, probably like whatever they bring out, we know. However, the logic and like, the sort of like new ways to obfuscate itself, we're probably going to start to see like, that sort of new obfuscation, right? Something that we actually just figured out recently is the fact that, and probably I'm digressing a little bit here, was before, in a sandbox, most of like what malware would look like is, am I in a VM? I'm just going to look for like classical signature. What is a VM, right? And things like that. But now we're seeing that, they will look for evidence of like you having some kind of AI, right? Why? Because if a sandbox does not have AI, it's definitely a sandbox. It's not human, because we all have some AI features on our devices today. Like if you search your device, you have Copilot, you have some libraries related to or Llama and all that stuff. So we have a lot of AI features as humans. So if I'm attacking victim, and if you don't have an AI, like that is a sandbox. That is not a victim, right? So then the malware will not do anything, right? So it's sort of crazy. And I was talking to that other lady, and again, I didn't see this in practice. I was like, probably I shouldn't say this. Okay, I hope I don't put myself in trouble. But again, this is assume this is a research lab. Okay, so if I am designing malware, I'll probably design a shell. Like I'll just design a shell, not as a terminal shell, just kind of a shell of the malware with nothing in it, apart from probably like an exploit also exploiting some vulnerability. But when I get onto the host, with everybody having some kind of like piece AI enabled pieces and whatnot, I'm going to create the malware on the device, right? Because I don't have to load, I don't have to communicate to my CNC server to like get the malware. I'm literally going to be able to say, if you're running some kind of local model or you have some kind of plugged-in API for Claude, I'm going to use that. If I maybe escalate some privilege of what you have, I'm going to use that to create the payload on your device. And that I can use that to spread. So there are no more gadgets for the offense. I'm sure, like, and again, the thing is like, defense is always coming in and saying, oh yeah, we've seen this, we're going to defend it, right? The mindset is changing now. People are like, okay, what will likely be? And this is where research comes in. There are new research and saying, okay, this is what the new malware will look like. And then so defense will start to look, okay, how do we defend it? But generally offenders are just looking for like that one thing, right? They're not looking to protect the billion people. I don't know if that is silver line.
Oh, no, thank you very much. That was very helpful.
Yes.
But in the automated analysis, I was thinking, longer changes.
Oh yeah, actually, in fact, homomorphism is the real reason why sandboxes started to exist. Because before, when you start with that code reversing, and then we can get like hashes from like the reverse code, but then the malware started having that sort of obfuscation and like or not even some obfuscation, right? So, but when you run it in a sandbox, if the malware does not know that this is sandbox, it assumes this is the tip, then it's just going to go do whatever it's supposed to do, right? And so because it's doing what it's supposed to do, you can take them and you can read the logs, you can trace system calls, you can read memory, you can read registers, so you can literally be able to split the behavior of the malware. Having talked about this, but you can use memory forensics as another tool. So in memory forensics, like you leave the malware to on, take this snapshot on the VM at the point in time, and normally, even if take an example, a program is encrypted. When it is encrypted, at one time it has a decrypt, right? So if decrypted stuff is going to write the code in the code section in memory, right? I mean, you run this on a data section in code section, so it's going to write in some code section. So when you take memory forensics, you take a snapshot, that means you can dump the decrypted code from memory, which technically you don't have access to. So pretty much like most of what we have in terms of application, like IDA is supposed to help with that. But again, the anti-analysis is used because kind of like added. In fact, anti-analysis is often not called obfuscation, but it's called evasion, or because we want to kind of differentiate the issues. Yes.
Okay, so like in terms of like prior pre-AI, so like atmosphere versus the malware and ACSAC, do you consider like current time being like this model versus this model? And if so, like where do you see like the catalyst and prediction for like maybe the next 5 years, probably about malware development and y'all can miss that.
So I actually did not put that here, but I put it and then I removed it. Okay. It's about prediction. I did see prediction in terms of like number of samples, but I can tell you like I was kind of looking for what's going to be the prediction in like 2030. I couldn't get like a good kind of data source, but I found a projection for malware analysis market. It's kind of crazy, right? Malware analysis market. It shows that the market is going to be about $76 billion by 2030. If the market is going to go, actually probably going to show this. If the market is, oh, did I delete it? Oh, okay. It was somewhere here before. But if the market, I think the market was, I can't remember the number, but I think it's like 12 billion in 2012 or somewhere. I can't remember like when it started, but I know about 2024 is going to hit 76 billion. This is in terms of good solution services. So it's like, if the market is showing that upward trajectory, it means like we're expecting to see more, kind of malware in that space. As an example, also, I kind of mentioned like, I've not seen any research work or any real malware in the wild that is using like, our local models as a gadget. But I can tell you from my perspective, I've been in this space for a while, if I am designing malware, I'm going to definitely be using like, the model that you have on your machine to produce samples. So we can kind of see that, okay, that there's going to be a shift in terms of how the samples are created. Just to kind of give you maybe historical background on this. When malware started, there were usually more viruses, right? So the way virus works is you take a Windows application and then you sort of inject the virus. So we said that viruses, they don't have they're not self-contained, but they're self-propagated because they're usually kind of a stop. So you can inject the stop. Usually they can use like fragmentation or whatnot to just kind of inject itself into a benign, notepad with exe, and then then now your notepad is safe. But they can propagate to the next device. Now, gradually, we started having worms where the worms, they are self-propagated and self-contained, not self-contained, self-propagated, and they can move across different machines, like through the network or devices. And then we moved to more Trojans where the payload is embedded inside. It's always embedded inside. Now, fast forward, we started to see more malware that are like in the rootkit space, where they infect you with like, that initial infection vector, and then they make a communication to the CSV server to download the payload. So like when you analyze the initial vector, there is no payload. They're completely like absolutely no payload. The payload is inserted later. Usually, kind of like the time between the initial infection and the payload is not too long. Then we move to APTs. Where in advanced persistent threat, what you have, and this is usually what you see in nation state actors and affecting critical infrastructure, you see that the malware usually will stay in your network for a very long time to do reconnaissance and understand your devices and understand like your network architecture, like who does what, the people, the users we have and whatnot, before they then load the payload, right? So there is that time frame for reconnaissance. If you've ever read about Stuxnet, how many of you have not about? Yeah. So Stuxnet is like that kind of one malware, kind of it's an APT malware, but like it did a reconnaissance for almost like 5 years. Started about 2006, did not do that to infection, right? So we see that, and then so now we're probably going to get to a place where why would the malware want to download the payload from somewhere when you have the gadgets for that? Right? So I can just like create the payload like on your machine. So that way, like all your NIDS network IDs. So all your NIDS is useless. All your EDR that are like trying to protect whatever you're going to install is useless because then you don't even have clear signature. Like they're going to create a version of the payload for you. They're going to create my version for me, his version for me, right? Based on like whatever we have going on our machine. So we're going to start to see like real changes in terms of like once a month. It's not scary. I don't think it's scary.
I know we asked a lot of questions. I have an opinion. I need to go. So let's take malware. Do you honestly think, because I don't know that they're one of the people that spread that stuff being applied to them. Do you believe that this,
What?
like, they are one of the companies that produce malware device,
Huh.
device.
Why do I trust them? No. Okay, so if you ask me, so if the question, if you ask me whether I trust antiviruses, it's not. Like in general, I think like sort of like that is really what that. I believe like the market for antivirus. Y'all agree with me? So defenders and normal EDRs that comes shipped with your devices are not necessarily your usual antivirus that we know anymore, right? So it's sort of different. I mean, you probably cannot turn off your Windows Defender. It's part of your Microsoft. And Microsoft knew that they did a very, very bad job for many, many, I'm not against Microsoft, but they did a very bad job for many, many years, right? So they kind of like, trying to redeem themselves with like, okay, now, our Defender is doing well and whatnot. I think there is the part of like technology has to protect you, technology should protect you, but there's also the human angle to cybersecurity that I think is often like benefited to the side. A lot of infection could be prevented with like human non-human cybersecurity. Because there are sites you don't have to know, there are things you don't have to do. I don't have to download draw.exe, right? I can test to see, my UAC is telling me like, don't start this, like it's not from a known publisher. But yeah, I don't care, I just install it. So there are things that are the normal human side. But again, the knowledge though, on the human side defense, the knowledge is evolving so fast. Technology is like evolving so fast. I mean, think about like, we're kind of like struggling with like, laptops and iPad and then now mobile and IoT and like, my grandma will have like a smart thermostat and then, something happened to that, right? So there are so many things to think about and, the human side is just not catching up to that. I run the cybersecurity clinic and I talk to small businesses about cyber hygiene, particularly like that's what we do in the clinic. We do seminars for small business, talk to them about, how to protect their network, how to protect their businesses from cybersecurity, from kind of cyber incidents. And I can tell you that it's hard for them. It's like, what do I deal with? The cybersecurity is not my business. Like it's a debt for me. Like it's not. I'm studying cost. Like that is my business. It's not cybersecurity, right? Probably, if something happens, I'm going to deal with it at that time because they have to deal with so many. So it's sort of like, I don't know. Maybe we can all come up with some solution. I don't think there's a solution. All right. Thank you so much for having me. I really appreciate it.
All right. Thank you so much for coming for that talk. I know that there were a lot of great questions, a lot of good questions. So that's always the sign of a great talk. We appreciate you coming. We're thankful that you were able to join us. I'm thankful for everyone who's here. And we have the crawfish boil right after this across the street. So make sure you gather your things and we'll see everyone at the crawfish boil.